Okay, let us start our first lecture. As I promised you, I wanna record first lecture as an offline platform with more quality. Actually, this lecture is would be it would be necessary for following our lecture in the future and lectures of the Ivan Mitrofanov. And today we need we only discuss about some simple concepts and definition. So and define very important terminology, I mean full shifts. So let's do together. Okay, right now I want to make a connection with real analysis and actually symbolic dynamics, and I will sometimes it's some connection also with combinatorics and word. Let me take my pen. For example, we have some connection with continued fractions. New a fractions. And for example, what's the connection with, or what is a connection of continued fractions with concept of symbolic dynamics? Okay, let's suppose, for example, we have one rational number like 415 over 93. Okay, we can denote that approximate, with another notion. This fraction is approximately 4 point blah blah blah, something like that. It's approximate, it would be equal to 4.46 and so on. So, by the way, we can denote it with another notion. You know that from high school or some elementary number theory courses, we can denote it by this notion. Okay, by continuously division, we can have it. So we can write, just a moment, with this notation. 4 in it is integer part. After that, I put this and 2 here, then 6 here. 4, 2, 6, and 7. If I give you this number, so it means you have this number. So in this situation, we have some symbol, or for positive rational number, we can use this word. It is right now we have one word with 4 letters and or 4 symbol. Actually, if we want to discuss about continued fractions, positive and show there's positive real numbers, we need only these symbols. 0, this 0, 1, 2 till 9. And actually, if we want to, for example, show some this symbol, we can also consider these symbols, but it doesn't matter. It depends how you are very sensible or not. By the way, it's one relationship between symbolic dynamics, combinatorics on word, and real numbers and number theory. Let me discuss another simple example. Also, you can also discuss about some general real number. For example, if we, oops, for example, we are familiar, all of us with familiar, for example, E, and if we consider it as a sequence, I mean the limit of one sequence, we can say that it would be, first of all, in this sequence, it would be convergence to E, 1, 2.1, 2.1, 1, sorry, 2.1, 2, then again 2.1, 2, 1, and again 2.1, 2, 1, 1, and 2.1 to 114, and so on. So, but you can consider like one word, this number like as a continued fractions in this notation: 2, 1, 2, 1, and so on. Later we will see that it would be like actually one infinite word. Okay, so we can consider that all of the real numbers is like a one word, infinite word or finite word. It's dependent on that it would be rational or irrational, it's natural or not natural, and so on. So here is the or symbol is a number, or also, for example, we can one fraction, we can consider that, for example, this number would be like one word. Later we exactly understand what is exactly word. It would be, it is has a free symbol. The symbol of that is one, these guys, and these guys, and so on. So right now we have one example. Understand so what's going on, what is a story. Let's go to the next example. Okay, here it's related to computers, and I want to understand how computers store data, but not technically. We want to again understand the computer is using the word symbols to make understood and understand some data and analysis, or to compile some things for you. Okay, so actually we can say that computer store the data with as a sequence of 0 and 1. Okay, the symbols is 0 and 1, and the computer store all of the data. For example, for the number 2, it would be stores like, for example, like this. It's binary notation, or for example, it would be equal to 2, and also, for example, 3. You know better than it is very easy to pick things and easy things. By the way, so it stores everything by this some sequence of 0, as a sequence of 0 and 1. That's it. What about the next example? Okay, it's compact audio, and actually clear. Actually, it's the picture of the Beethoven, but I want to say that how the gramophones and the compact audio disc workings, they use blocks, or actually blocks of 0 and 1. Actually, black is means word. I mean finite sequence. So they use finite sequence, finite sequence or word. They are the same meaning, these things. Or this book, majority times you use this terminology, black. All of them is the same. And representation signal for representation signal samples with and the or symbols, it would be 0 and 1. Okay, that's why it's like, for example, to digitally record Beethoven symphonies and symphonies. So it's another example. So in the previous example, I clear that. The previous example, we use the infinite words, and the symbol is 0 and 1. And in this example, for real number, it's infinite words or infinite sequence, and the symbol is 0, floating point, and 0 till 9. Okay, 1-digit numbers. So let's go to the next concepts. Okay, right now we have some basic terminology here. First of all, definition of the alphabet. I draw my pen. Okay. Actually, alphabet is a finite state, like 0 and 1, like A, B, C, A, or some notation, like up, down, right, left, and so on. So, you see that many times you see that we use this concept when you want to use some bijective bijection counting. For example, when you want to count the number of subset of one set. For example, if you have one set like this, 1, 2, 3, you denoted by 0, 1 quotes like this, and it means you have this subset. You don't have 1, you have 2, and you don't have 3, so it would be like 3, this subset. By the way, and you decoding using coding and for pure counting. So it's one of the application of the using alphabet and in combinatorics, but we don't need too much for here. So what about finite word or block? We also use block, or roughly speaking also without using infinite and finite. In this book we use also word, especially in combinatorics and word. A finite words over alphabet A of length L, non-negative number L, is a map from 0 to L minus 1 to our alphabet. Let's suppose, for example, all alphabet is A and B. Okay, one block or word, it would be like function. I need to, for example, one word with length of 3 is 0, 1, 2. I mean length of L, it would be 0 to L minus 1. So length of 3 is 0 till 2 or alphabet A. Okay, but what is the relation of our function? It would be like this. W of 0, it would be equal to A. For example, W of 1, it would be equal to B, and W of 2, it would equal to, for example, again B. It means in the position 0, here we consider this position 0, position 1, position 2. In the position 0, you need to put A. In the position 1, you need to put B. In the position 2, you need to put B. So your word, it would be equal to A, B, B. And the length of one word, it would be the number of the letters appearance in that. So an infinite words over A is a map from the natural number And majority of time we consider that in this course, the natural number is not beginning from the one, it's beginning from the 0. Okay, so where A is a map from natural number to our alphabet. Okay, and by infinite words or sequence, sometimes say that instead of when we are talking about infinite objects in symbolic domains and combinatorics of word, we use instead of the this vocabulary sequence. So, and by infinite words over A is a map from the integer numbers to our alpha. So, alpha is one important remark, not very important, but we need to know that alpha in the real life sequence of symbols are finite. Okay, it means the alphabet, it would be finite, and it's often extremely useful to treat to line sequence as an infinite in both directions. I mean, for example, later we can talk about more about that. We consider as a each position of the, for example, each position of the letter as a time. For example, later we will see that, for example, if, for example, here is position 0, and here is position 1, and here is position -1, and here position -2, and here position 2, and so on. Here is it, for example, present, and here is one, for example, second in the future, later, and here is 2, for example, second later, and here is 1 second before, and here is 2 seconds before, something like that. Okay, it's like it has a connection with discrete dynamical systems and discrete times. So, okay, a question. Actually, what is the main object you will be studying in the symbolic dynamics? Actually, our principal objects of study will be the collection of, as I told you, by infinite sequence of the symbol from the one finite alphabet. Okay, very good. Actually, more officially, by infinite sequence or by infinite word is denoted by this notation, and the index comes from the integer number. Or you write here, like for example here, it's each of them, they are the letter, and this guy's xi's inside of the or alphabet. Okay, for I inside of this. So actually, when writing a specific sequence, not with the index, when we don't have an index of them, we need to specify where is exactly the position of x0. We use by some point. For example, let's I want to write a 1 by infinite sequence like a w or x. It would be like this. It would be 1, 2, 3, 4, and here 5, 6, and so on. So I don't know which position. It's both sides. We have two directions from right to left. It's by infinite sequence, but we don't know which letter is standing in the 0 position, which letter is standing from the 1 position, and so on, first position, and so on. So that's why we need to put 1 point before the position of the 0 position. So here it would be x0, here it would be x minus, and here it would be x2, and so on. Okay, so okay, let's have some more definition and maybe more technical definition. Actually, okay, let A is a finite alphabet. The full A shift is a collection of all by infinite sequence of symbol from A. Okay, so it means if you have one alphabet like A, you have a two letters. I mean the cardinality of our alphabet would be 2. So if you write all of the by infinite verbs inside of the one set, it would be full A shift. Okay, so like here we denoted by this notation, it would be, for example, A power Z, it would be equal to AB power Z. It would be like this. Okay, it means X is equal to XI to Z, such that XI is equal A or B for all I inside of this. Okay, so it means you need to put all of the by infinite sequence. For example, A B B B B B A B B B B B, and you need to put 0. For example, here, floating point here, and so on. All of the such this thing you put in the one subset, and all of them we can consider it is full A shift when your alphabet will be A and 0. So, and we have a special type of the full shift, and we say that the full R shift or simple R shift is the full shift over the alphabet 0 till R minus 1. So one important thing as a remark that I see that I will put. Okay. One more thing you should know as a remark. So as a remark, we can say that. As a remark, we can say that as a remark, we can say that if cardinality of your alphabet, it would be R, so it would be, you can find a bijective map or bijection relation between this shift and to A full shift. So if cardinality of A or your alphabet, it would be, for example, A, it would be like this, A1, just like other symbols, not the numbers, to AR, then you have a bijection corresponding between full, in this case, let I write with green color all of the stops. It would be full A shift with full R shift. Okay, so the full A shift is denoted by this notation. So let's clear all of the board. Okay, let's go to the next slide. Okay, so let me check that I will explain everything. And also, we say that in space we have a special sequence. We say that. Let me. Okay, and also full to shift. We call that binary sequence. Okay, it's a special type of the actually shift. We say that full to shift. Then our alphabet is 0 and so some computer using two-side binary sequence, they are using full to shift. maybe I don't know, I'm not expert in computer science, but maybe we have some computers to using such this sequences. So let's go to the next slide. Okay, as I told you, a block or word or alphabet is a finite sequence of the symbol A, and the sequence of the no symbols, it's called empty block or empty words, and denoted by epsilon. And the length of the word or block like U is the number of the symbol it's contained in that. It's contains or in contained in that. So, and we denoted by this notation like absolute value, and the length of empty void, it would be 0. And and one more notation, the set of all k blocks over A, it's denoted by this notation. So what does it mean, AK? It means all of the word U such that U, it would be equal to x0, x1 till xk minus 1, such that xi is side of the A for all I is equal to 1 to 0 to k minus 1. Okay, so this is one notation. So as an example, a very simple example, you can you can count if the number of the cardinality of the this guys, it would be, for example, equal to R. What is the cardinality of this guy? Discuss about this problem. Okay, so let's go to the next slide. Okay, right now we want to talk about subword or sub-block. Okay, so okay, a sub-block or subword of U is A1, A2, AK is a block of the form like this. I mean, for example, if you have one word like A, B, C, D, E, F, G, and so on, you need to cut some consequence letter. That's why it would be like one subword. But here, this is not a one subword or subblock A, B, F, G, for example. It is not sub. For example, it is W1 is not one sub. Okay, so we need to select it consequence number. Also, the right infinite sequence. Actually, we can have a one right infinite sequence. One more thing, if you have a one infinite sequence like x, I mean x, it would be x, let's say write like this way, x1, x2, x3, and so on, x0, x minus 1, so on. We can cut, for example, from here, and we have one block. Like, for example, we use this notation, x now, for example, xij, when I it's actually bigger than less than j, it would be xi plus 1, it would be xj1 infinite word. And if we use this notation, I and j, it means we don't have a j yet. So it would be like 1i, I plus 1 till x, j minus 1. Okay. Also, we have a right infinite sequence. It will be cut from I to the right hand side. I mean this notation. Let's say change my color. X I to infinity. It would be like xi plus 1, so on. It's only basic terminology. We need that in the future. Also, left hand side, oops, minus infinity to I, it would be like I, xi minus 1, xi minus 2, so on. And we have another notion in the central 2k plus 1 block or word. It would be like, we denoted by this notation, and it would be like x minus k minus k plus 1 till xk. Okay, right now you have a, actually why we say that 2 class 1 block, because we can say that the length of this guy, actually it is 2 class plus 1. So we right now we learned some basic definition here. Let's go to other concepts. Okay, actually we can make a connection with two words or two blocks, I mean operation on the words. It's one operation we introduced to you here. Two blocks U and V can be put together, stick together, or concatenate by writing U first and V after that, like UV. Okay, for example, if A, it would W, it would be, for example, AB, and U, it would be, for example, CD, a concatenation of U. I do use this notation right, and later we don't need to put that. It would be ABCD. Okay, so generally this is one of the binary operation from this guy. This notation means all of the finite alphabet over this all of the finite words over this alphabet times these guys to again this guys. And this notation, it means all of the finite word without empty word. So okay, so it means if you this guy, for example W, it would be you put together. So it has some property. Actually, the length of that, if you the length of UV, it would be equal to length of U plus length of V, and it would be not communicate. I mean UV, it's not always equal to V U. You can see here U star W is CDRB and it's not equal to them. So it has identity element. Identity element is this. So it means U, this guy, it would be equal to this guy, and it would be equal to U. Also, they have associative property. I mean U where W, it would be like U where W, and you can eliminate the parentheses and you can write, because of it has this property, UVW. So it is binary operation, and it is as an associative property and as an identity element, so it would be one monoid. Okay, this structure it would be like monoid, and this structure without identity element, it would be like semigroup. Okay. So right now we have one algebraic structure, but we don't need that too much here. And another things, we can stick one word many times together, like power. For example, um, it means m times you operate this concatenation operator. Okay, m times, and that's why it has some property of the power. You can check that by yourself. Okay, so also we can say that u0 is equal to epsilon, and u infinity, it means u is point of 0 position, u and this guy. So we have such this concept. Let's go to another example. It's another definition. It's very important for us. Let's clear. Okay. The definition is very important. Shift map. A shift map, sigma, and the full shift. A. Actually, it is a map a point x to the point y is equal to sigma of x, whose I coordinate is equal to this guy. So actually we can say that this operator, it would be like this, and we denoted by this relation. We have 1 by infinite volts, and I will give you another infinite volts. Okay, so okay, so let I explain for you what is the exactly infinite volts. Sorry, what is exactly shift volts by some more detail. Let's you have a one volt by infinite sequence, and you act this in this map sigma to y is equal to sigma of x. Okay, let's I write all of the letter of this by infinite sequence: x0, x1, x2, x3, and so on. Okay, x minus 1, x minus 2, and so on. So okay, let's I do like this guy between this, like gel or cell. Okay, right now it means if we are acting the shift map, this guy goes to this guy, this position. This guy goes to this position. Oops, this position, and this guy goes to this position. This guy goes to this position. This guy goes to this position, and this guy goes to this position. Okay, it's right now a little bit clear. But you can see it would be like it has an inverse, actually it's injective, and also is surjective. And actually you can see if I will give you and you act like inverse, okay, and I give you y, you can find it at exactly x. Okay, so each position you can go to the back So it means the inverse is exist, and it would be like bijective. So you can write with more detail. Also, you can compose it. And one more time, you can, for example, compose it shift map, like here, one more times. And here, if you act at the moment, at one time, it put is sigma 2, it means, for example, this guy is also, let I change my color, this guy comes here, x minus 1, and this guy come here, x0, and this guy comes here, I mean x1, and this guy comes here, x2, and you do simultaneously 2 times. So it would be 2 power. And generally, sigma k, it would be k times composite of these guys. And the relationship of that, k time, let me write here with more detail, sigma k, it would be one function from a, full shift, full shift a to this guy, and such that sigma of kx, I mean y, sigma yi is equal to xi plus k. Okay, so it means k times I doing that. So also we can define thing. So also we can define other stuffs. Okay. I mean the inverse k, it would be inverse minus k. Okay. Okay, let's discuss about other definition or concepts. We need that in the future. Okay. And the definition, first definition, not first definition. Right now, you need to discuss about some concept. Actually, sorry. A point x is a periodic for sigma if sigma pi, if we find the one positive integer number like n, such that if you compose it n times a shift map, it would be equal to x. And we say that x has a period n under z. And if x is periodic, the smallest positive integer n, for which sigma power n is equal to x, is the least period of x. Also, if sigma x, I mean n is equal, in the special case of that, n is equal to 1, the sigma of x is equal to x, then x is called the fixed point for sigma x. So right now it says we know, maybe you know that, majority of you know that, but we need to know them. Actually, and some important fact, we need to use them for solving some problem. Okay, first of all, if x has a least period k, then it has the period 2k, 3k, and every period of x is a multiple of k. So, like for example, if you can say that, like for example, you have one x. Anyway, like for example, AB, 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 and so on. Right now I consider that one side infinite word or sequence, but for 2k by infinite also it's satisfy and verify. So the length of period it would be 2, but if you consider that the length of that is would be 2, but 2 times 2, I mean 4 also, it's satisfy. 6 also satisfy. Okay. So it is another important thing. And what about others? And a fixed point for sigma, I mean full shift map, sigma must have the form these guys for the symbol A. I mean, it would be like all of the fixed point over full shift. It would be like, for example, if our alphabet, it would be like this, then it would be like A, and also B, 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 B. It means we have two fixed points here. When our alphabet, the cardinal letter of all alphabet is equal to 2. And a point of period n has the form this guy. When n belong for some n belong q. So it means you have a one word with length of n, I mean the length of u, it would be n, I mean u, it would be equal to, for example, x0, x1 till xn minus 1, and u n time like this, you put together. Okay, so it's this main concept. I will record another part of this first lecture, and I will also upload some it is basic things what I will upload some seminar question. Okay, see you for next part.